Hey, Chem30s, it's Manchak here. This is your video lesson for concept D1, the very beginning of Unit D for us, looking at equilibrium systems and getting into some more stuff related to acids and bases. So to this point in this week, you should have covered concept C8, which was the very end of polymers and polymerization, the end of our Unit C organic chemistry unit. Now you guys are shifting into doing Unit D, which is on equilibrium. So what I'm going to do today is a very, very short lesson on what equilibrium is and talking about the different kinds of equilibrium that we have. And then we're going to start to focus in on chemical equilibrium, which is the one that's going to be what we're paying attention to for the rest of this unit. So just to look at our outcomes for this section, then we've now shifted into Unit D, which is called Chemical Equilibrium, focusing on acid-base systems. In general, we're going to be looking at two very general outcomes in this unit. One is to explain that there's a balance of opposing reactions in a chemical equilibrium system, and we're going to try to explore that idea from a bunch of different angles to try to get a sense to what that actually means. We're going to explain it qualitatively, so we'll look at properties and we'll look at explaining things through observation, and then we will also look at it quantitatively, where we'll actually assign some numbers to these equilibriums. Then we're going to look at the quantitative relationships in simple equilibrium systems, and we're going to use acids and bases as our model for that and have a look at what goes on there to try to deepen our understanding of what's going on with acids and bases. And what's really interesting to me is that as we've moved through Science 10, Chem 20 now into Chem 30, acids and bases have come up in each course, and we've gotten a little bit deeper and deeper and deeper into understanding what acids and bases are. For this video lesson, we're focusing on concept D1, which has us defining equilibrium, what it is, and we should have a good definition already because any course that you've done with me, we've talked about equilibrium at some point. And then we're going to state the criteria that apply to a chemical equilibrium system. So, for example, it's got to be a closed system. There's got to be constant properties, equal rates of forward and reverse reactions. In other words, we're going to just generally define what a chemical equilibrium is, and we're going to compare it to some other kinds of equilibria that we've talked about elsewhere in other courses. So just to sort of hash through some of the stuff that I need you guys to know. So this is going to be very, very short. We're going to talk about an introduction to the unit, which is kind of what I just did. And then we'll talk about what equilibrium is, and we'll explore solution, phase, and chemical equilibrium. And then video number 2 that we have down here, this video at the bottom here is the video that I'd like you guys to look at. It's a much longer video. You can watch from the beginning to about 2 minutes 40 seconds, and we'll get into the rest of it later on. So if you wanted to continue on the rest of the way through it, by all means do that. And it will be a preview then for what we're going to cover in D2 and D3 next week, those kinds of things. There's nothing in particular that I'm going to have you guys do as far as practice work goes, but just I'd like you to make sure you're focusing on learning your definition of what a chemical equilibrium is, and then know the differences between chemical, solution, and phase equilibrium or state equilibrium, just so that we can handle that. I'll have a short formative quiz for you guys to do up on the Google Classroom, wait for feedback, and then jump into the summative quiz. So I think from now, let's move into the actual lesson part of things, and I'll get myself moved out of the way, and then we'll go from there. So we're moving into equilibrium in acid and base systems. This is Unit D. We're going to cover, in this unit, the concept that chemical change eventually attains equilibrium is developed, followed by a focus on quantitative treatment of reaction systems involving acid-base solutions. So that's going to be the second half of the unit. First half, really, what we're going to do is lay down a lot of the theoretical background of the unit in the first couple of concepts. We'll start to quantify things in a small way. We're going to learn a tool called an ICE table that's going to help us organize our thoughts as we start to work through these equilibrium calculations. And then we're going to transition into concept D3, which I think is the hardest concept maybe in the entire year, because it's very theoretical, and it's quite abstract in well, relatively abstract in the way you have to think your way through it. So watch out for that concept. It's called Le Chatelier's principle. I will get into it in detail as much as I can with some supporting videos to help you guys out with it, because I find it's the one, for me at least, that I have the most trouble thinking my way through and really mastering. So let's move on. So these are our main objectives, and we've already talked about those up on the screen here. The questions that you should be able to answer by the end of this unit when we get there: what's happening in a system at equilibrium? And we should be able to answer that one actually by the end of this lesson. Try to create a visualization of what's going on there. How do scientists predict shifts in the equilibrium of a system? That's kind of Le Chatelier's principle, concept D3. And then we'll talk about Bronsted-Lowry acids and bases and how those work in, and that's adding on to our definition of acids and bases as we move forward. So concept D1 is going to be very short, and we're going to make sure that we cover it relatively quickly, and then get you done for this week and get you ready for next week. So we're going to define the equilibrium and state the criteria that apply to what an equilibrium is, and that's really concept D1. Then we're going to get into, in concept D2, which will be next week, identifying, writing, and interpreting chemical equations for systems at equilibrium, and then we're going to define Kc and write the equilibrium law expressions. So we're going to get into that next week, not this week. So really, our objective for this week is to really get a good solid definition of what an equilibrium system is. So let's move on. So something to keep in mind. When we are referring to chemical systems in this unit, we're going to be referring to them as closed systems, okay? Meaning that matter is not going to be able to escape, okay? So working with closed systems isolated from their surroundings, allows us really then to focus on the properties and conditions that change much more easily. So if we try to let things open up, what we're going to find as we move through this is that if we add more of a substance or take some of a substance away, what's going to end up happening is that's going to mess with our equilibrium and change what's going on in the system. So we're going to try to hold things more or less constant and then have little changes along the way to see what happens to these systems as we play with them. Earlier in chemistry, so we're talking now closed systems at equilibrium. Earlier in your chemistry learning, we told you that reactions are always spontaneous, they happen fast, they're quantitative, and they're stoichiometric. Okay, and I told you guys this back in Chem 20 when we did Unit D in Chem 20, and we worked our way through that. And I think I may have even said at that point that, you know, I'm telling you this for now, and it's true all the time until we get to Chem 30, right? And I also believe that we've spent some time debunking some of these myths as well. If you recall, in the last unit, we talked about spontaneity of reactions, right? Particularly redox reactions, but we know that not all reactions are spontaneous, correct? Some of them are non-spontaneous and require a little bit of input of energy in order for something to happen. Not all reactions are rapid. Some of them take quite a bit of time to happen because they don't have a lot of input energy. They don't take place quickly enough. Maybe they need a catalyst or something along those lines that we talked about in Unit A to make them happen a little bit more quickly than would happen normally. We also said that all reactions are quantitative, and this is a myth that we're going to dispel in this unit. And one that we won't dispel is that they're stoichiometric. Stoichiometric all has to do with the fact that when we have whole number coefficients inside that reaction, we can relate chemicals to each other. So we've started so far dispelling a few of these myths, and we'll continue to dispel particularly this one, the quantitative one in this unit as well. We also led you to believe that reactions always occurred in a forward direction, from reactants to products, okay? So we always progress from left to right. We found out briefly, if you think back to Unit B, that when we were dealing with our table of relative strengths of oxidizing and reducing agents, this table here on page 7, we did find out in that unit, though, that that's not necessarily true. We do actually have a difference. Sometimes a reaction could be read left to right, or it could be read right to left, depending on the situation we put it in. This is what we're going to start to play around with in this unit a little bit, okay? So the final state of a closed system can be explained as a competition between collisions of reactants to form products and collisions of products to form reactants. If you guys can, I would encourage you right now to grab your pen or your highlighter and maybe put a circle around this, because this is our definition of equilibrium. Equilibrium is the final state of a closed system where there is a balance. Equilibrium is a balance where there is a balance between reactants colliding to make products and products colliding to make reactants. So if we use this example at the bottom here, sodium sulfate and calcium chloride reacting to form calcium sulfate and sodium chloride, notice that we've inserted a double arrow here. That double arrow indicates that there's a balance between, this reaction is reversible. It can run forwards, it can run backwards, and it's also going to be an indication for us that we've got some sort of equilibrium being established here. When this chemical system establishes equilibrium, there's a balance between a sodium sulfate and a calcium chloride bouncing off of each other to make these guys. And for every 2 of these molecules that collide to make those, 2 of these molecules will collide to make those. Does that kind of make sense? So there's a balance between the forward and the reverse reaction. If we get 5 forward reactions at equilibrium, then we should get 5 reverse reactions at equilibrium. Okay, that's what a chemical equilibrium is. Does that make sense? Okay, if it doesn't, watch the video that I linked in the Google Classroom, or track me down and ask a question. So, a couple of things that I want to talk about then. Any closed chemical system with no observable change occurring is in a state of equilibrium. Okay, so if there's no observable change, you sit there, you stare at it, you put a video camera on it, you watch it for minutes or hours and nothing changes, we can say that it's at a state of equilibrium. There's 3 kinds of equilibrium that I want to talk about with you guys: phase, solution, and chemical reaction. And it's this one at the bottom here where we're going to spend our time in the unit, but I do need you to be aware of these 2 as well. So phase equilibrium involves a single chemical substance existing in more than one phase. Think of a phase as a state, so solid, liquid, or gas, in a closed system. So a great example of this is water in a sealed container. Okay, you let that water sit there, come up to whatever temperature the room is at, and it's going to have a balance that's struck. Some of the water is going to evaporate up off of the surface of the liquid and end up condensing inside that closed container, and falling down. So the evaporating to gaseous form is one example, going from liquid to gas. Then it condenses. That's maybe our reverse reaction, and turns back from liquid to gas. So it goes gas to liquid, liquid to gas. Okay, that would be a phase equilibrium. And we might write a chemical equation, to represent that. Is we would have H2O, in my very poor writing, in a liquid state, would be at a phase equilibrium. So I'm going to write those double arrows with gaseous H2O here. Okay. So we're going to say then that in this state, we have a balance between the forward and the reverse reactions. Balance between water turning from liquid to gas and gas turning to liquid. Okay, that's what we're talking about with a phase equilibrium. A solubility equilibrium we actually talked about back in Unit C in Chem 20 when we were talking about saturated solutions. Okay, so notice how I mentioned saturated solutions here. So in a saturated solution, we know that it's saturated because there is a balance between entities coming from a solid form and going into an aqueous form, and vice versa, right? So if we had a solution of, let's say, sodium chloride, and we created that solution, there would be a balance then between not 2 phases necessarily, but between dissolving, that should have been an A, balance between dissolving and recrystallizing. So those terms should sound familiar from Chem 20. So in solubility equilibrium, one sodium chloride molecule or compound might dissolve and turn into an aqueous form, but then another one is going to turn from an aqueous form into a solid form. So what we might have is those sodium and chlorine ions being wrenched away from each other, and in some cases they might bounce up against each other and solidify again. So that's the balance that's taking place here. In a chemical reaction equilibrium, and this is where we're going to spend the bulk of our time in this unit, this involves several substances, the reactants and products of a chemical reaction, and then there's a balance in that reaction. Like we said in here, right? There's a balance between these two guys bumping into each other to produce some of this, and those bumping into each other to produce some of this. That is chemical reaction equilibrium. Just one last point, I believe, here on this, and then we're gonna call it done for this. So these three types of equilibrium are explained by what we call dynamic equilibrium, and the key word here is dynamic. So we know that equilibrium is that state of balance. Dynamic means that it's opposed by static. Static means there's no change; it just sits there and nothing changes. But I'm telling you right now, in these closed systems at equilibrium, there are changes. There's a balance between liquid turning to gas and gas turning to liquid. There's a balance between dissolved recrystallizing and recrystallized or something crystallized dissolving, right? Or there's a balance between the forward and the reverse reaction, okay? That's what dynamic equilibrium means from this perspective. We've explored dynamic equilibrium in biology before, where we've talked about the balance that we have in our bodies, for example, that tries to keep our blood sugar level maybe within a certain range. If it goes too far out or too far up or too far down, then we have things that bring it back into that range again. Okay, that's a dynamic equilibrium from a biological perspective. So this dynamic equilibrium then is that balance between two opposite processes occurring at the same time or at the same rate, right? So rate's probably better than time. So if we have two of something that goes from liquid to gas, then we will have two of something that goes from gas to liquid, and that maintains balance. But it's not static at this point, okay? Forward and reverse reactions are indicated by a double arrow, where left to right is the forward reaction and right to left is the reverse reaction. Don't get hung up on the fact that in my PowerPoint here, I've got the top arrow pointing right or left and the bottom arrow pointing right. I'm going to tend to write these if I show you guys examples like this. You are perfectly okay to write them like this, okay? Depending on where you go, you might have different expressions of that. Your data booklet has this one in it here. When you look at, for example, page 7, where we had our oxidation and reduction half reactions going on there. Okay, so I believe that's about it for this section. What we're going to do is transition into concept D2 next week, where we're going to dig a little bit deeper into how we can communicate a little bit more about equilibrium. For now, what I'd like you guys to do is go through and make sure you understand those three types of equilibrium I've talked about. So phase, solubility equilibrium, and chemical reaction equilibrium. Understand what we mean about dynamic equilibrium, understand the conditions, i.e. the fact that it needs to be a closed system for us to reach equilibrium. Go ahead and have a look at that stuff. Watch the crash course video up to, I think it was about 2 minutes 40 seconds. And then when you're done that, you should be maybe read through your notes a couple of times, and then you should be ready to do the practice quiz, wait for my feedback, do the summative quiz, and you're done for this week. So hope this all works out for you. Track me down if you have any questions. Stay healthy, and we'll talk soon when we get to concept D2.